So I'm going to present some work looking at how hospital population density can affect close contact in hospital and therefore the risk of respiratory infection. Why are we interested in hospital-acquired respiratory infections? Well, there's a real burden of infections. So 1 to 2% of all COVID infections were estimated to be hospital-acquired in the second wave in the UK. The contact rates within hospitals might be unusually high based on what we know about the contact patterns in general. And then the point that I'm going to get into mostly here is that hospitals might have fluctuating population density. And it's a reasonable assumption that a more crowded hospital will present more close contacts and therefore a greater risk of hospital-acquired infections that spread by close contact. When we model transmission, we are taking the messy reality and applying some simplifying assumptions to it in order to make a model like this, like a simple mechanistic model that we can use to understand the mechanics and to make predictions. And here, this is just a model with susceptible individuals and infected individuals. And one of the key assumptions that we are having to simplify is that of the contact between individuals. So the reality of contact is that it's a dynamic network with different types of contact. We make this simplifying assumption, and one of the most common assumptions that we make is that of homogeneous mixing, in which we assume that all individuals have equal access to all other individuals in the population, and that contact is governed by a contact rate. So that we can say that the force of infection or the infection rate is proportional to that contact rate, which may or may not depend on the population density and the other factors that go into the force of infection, so the proportion of infectious individuals and the probability of transmission per contact with an infectious individual. We can assume that they're not directly affected by the population density. So I'm going to focus on this contact rate, which we think might be. So what happens to the contact rate if we increase the population density? So if we go from this situation to this situation with the same proportion infected, but just a larger number, like a more dense population. So there's two typical assumptions. The first being that the contact rate will stay approximately the same, and this is known as frequency dependence. And the alternative assumption is that the contact rate will increase with density. And this is generally described as density dependence. And we can, if we look at these graphically, if we assume that the population density is going up, then under frequency dependence, the contact rate will stay approximately the same, and under a linear density dependence, it will increase linearly. But we can consider that this is actually a spectrum of dependence on density, where at one point you have the frequency dependence, where contact is not dependent on density, and this is most typical to model sexually transmitted infections, where we assume that the number of potentially infectious contacts doesn't double as the population density doubles. Whereas the linear density dependence, where contact is proportional to density, is more appropriate for modeling infections with an environmental exposure component. And so the question we're asking is, close contacts in hospital, where do they sit on this spectrum? So we came up with a formalism to describe the position on this spectrum, and that's by saying that the contact rate is proportional to n to the power of phi, this index parameter here. So where n is the population size or the population density, and phi is the parameter which determines where we are in the spectrum. So if phi is 0, this means that we're not dependent on density. If it's 1, then we're linearly dependent on density. But we can assume that typically the density dependence will be somewhere in between these two, or it's very likely to be in between these two. And we can also imagine situations in which it's less than 0 or greater than 1. And so if we plot this sort of partial density dependence on the same graph, then you would see something like this, where as the population density increases, the contact rate goes up, but not as much as under the linear density dependence. So this is where phi is 0 for independent of density, proportional, or somewhere in between the two. And so we have the opportunity to look at this based on the data from the NodsCov 2 study that Laura presented last time, which was conducted in 15 hospitals. And I won't go into too much detail, but it's based on the use of these wearable proximity sensors, which were worn by staff, patients, and visitors. And in that study, this was used these were used to estimate the contact rates between different types of individuals. So, and that's by contact rate, I mean the cumulative minutes in contact per hour spent on the ward. And this was done between, for example, patients and healthcare workers, etc. But this was aggregated over the whole time period of under which the study was conducted in each ward. Even though, so the opportunity in this data is that the population density wasn't constant over that time. So if we plot, this is just one ward. This is the study occurring over one ward, and we can plot the number of persons present over that time based on the number of active sensors that were being used. So we can see that it peaks in the first day. This is the daytime period. So it peaks in the first day, then it's lower at night, and then it peaks again in the second daytime. And so, and we for the purposes of this study, we're assuming that the number of people present is a proxy for the population density. And then we can also calculate the contact rate happening at each time point by looking at the total number of minutes of contact in each time point and dividing by the number of people present. So if we look at in a bit more detail, we can see that we can divide this. This is just a zoom in on an hour of the study. We can divide the time up into different time windows. So during which the population's size is constant. So this is one time window defined by somebody leaving at this time point and the next person leaving at this time point. But during that time, the number of persons present is fixed. So that becomes a time window in our data, and we can calculate the contact rate during that time window. So then if we take all of the time windows in our whole data set, we can put those, we can plot those graphically. So each point here represents a time window, and I've divided it up into day and night time because we're allowing for the possibility that the density dependence dynamics are different between the day and the night. And we can then try and fit those different models, so the frequency dependence, the linear density dependence, or a non-linear model to this data. So here you can see the frequency and density dependence, and then the frequency dependence is in blue, the flat line, the straight line is the linear density dependence, and then this curved line is the non-linear model that we fit. And what we can see here is that the relationship with density for the day and the night time is different. So when we estimate this phi value for the daytime, it's negative. So we see this negative dependence on density, whereas during the daytime it's positive. I'm going to show. So then what I'm showing here is that this is for each ward we can estimate that value of phi to describe where that ward sits on this spectrum of density dependence. So here you have phi is 0, which is when the population is the contact rate is not dependent on density, and here it's where it's 1 is where you have a linear dependence on density. And what we can see, well, first of all, there's quite a lot of variability that you can see within the estimates that we get. But then what was surprising to us is that you tend to see most of the points. This is during the daytime for all types of interactions, but you tend to see most of the points clustering around 0, suggesting that they are, broadly speaking, frequency dependent. So either the frequency dependence model was the best fitting model, or the estimated non-linear parameter was pretty close to 0, meaning it's not much different from frequency dependence. And then we've color coded the different points depending on which model fits best. So as they go from sort of dark blue to orange, it's when there's more dependence on density. So this is the daytime with all of the different types of interactions. But if we look at the nighttime, we start to see that there are some instances where there's much higher dependence on density. So there's a couple of instances where it seems like there's really high dependence on density, like much more than linear. But then there's also noise. Like in some instances, like pediatric emergency, you see when you look in the nighttime that it becomes negative. So it's obvious that it's a fairly noisy system. But I'll try and pick out some sort of general trends. So that's if we look at all interactions and how they depend on the entire population size present. But if we look just at how at the dependence on patient density, we can see here the way in which healthcare workers form contacts with patients as patient density goes up, and you see a lot more instances where there are these higher values. So like these orange values here and here, where there seems to be more density dependence, and then several instances where it's kind of it's in between frequency and density dependence. But anyway, it seems like it starts to deviate more from this sort of frequency dependent paradigm as when you consider just patient density. And then if we look at patient contact with patients, we see a lot of instances where you have very high density dependence up here in these orange points. And what we've then also done is to simulate what happens if you have a 10% increase in population size or in population density. What do you see happening to your overall contact rate, and therefore potentially your risk of contact-based infections? And we can see that with all types of interactions, then you don't see much change. A little bit more when you particularly in the nighttime, sorry, in the daytime. But when we look at the nighttime, we start to see a few more instances where you see greater density dependence and therefore greater increase in risk with a 10% population increase. And then if we look at healthcare workers forming contacts with patients, that starts to look a little bit more density dependent. And then if we consider patient-patient interactions, it seems to be a lot more density dependent. But it's obvious that there's a lot of, it's very noisy. So different types of ward, like different wards will have different it's pretty variable between the different types of wards. So to conclude, there's wide variation in the dynamics that we see, but many wards, when we consider all interactions together, many wards tend to show little or no density dependence. However, when we consider contact with patients, this does tend to be dependent on patient density, and particularly in the contacts that are formed by patients. So patients with patients seems to be fairly density dependent. And therefore, as a sort of direct consequence of that, a 10% increase in density seems to, according to this model, disproportionately increase the epidemic risk in many wards. And yeah, I'll stop there and I'll take any questions.
Merci beaucoup, George. Des questions? Ouais, Simon ou Lucia, je sais pas d'ailleurs. Le micro est coupé, hein, Simon.
Sorry, that's the habit somehow. Thank you very much for the talk. I just was curious. If I interpret correctly, it seems that sometimes the contact rate can decrease when the number of patients increase.
Sorry, I missed some of your words.
Non, on n'entend pas.
Could you repeat it?
Alors, on n'entend toujours pas, désolé, Simon.
Better?
Ah, ça y est, je crois. Ouais.
Vous m'entendez là?
Ouais, c'est parfait.
D'accord, excuse. Sorry. No, I was just, so here you can see that for some wards, if you increase the population size, you tend to decrease the contact rate. Is that right?
Yeah, that's the conclusion of that sometimes you have this negative dependence, which seems to decrease the contact rate when you have when you increase the population density.
And how? Because it sounds a bit counterintuitive, unless I'm misunderstand what the contact rate represents. But and how do you have an hypothesis for why this would be so?
I do think it's a little surprising. I don't think it's absurd though to think that I mean, just to speculate that people's behavior might change if they encounter like something that they perceive as a densely populated area versus a less densely populated area. And because this was conducted in the data collection was conducted in like April to June 2020, so it was a time when people were on high alert. So I mean that's obviously that is just speculation. We can't know exactly what it is that that contributes to that, but it does seem that that I mean, so the other thing I would say is that sometimes like we fit a variety of data sets to a pretty simple model. So it may be that there's a lot going on here that isn't captured by this simple relationship, but we can't know more than that.
And so for instance, the first points on the left mean that if there are only like 4 people in the ward, they're all going to be in contact with the 3 other people. That's what it represents.
It does seem to be the case, yeah. Like you often see this instance where when there's few people in the wards, you have like relatively high contact rate.
Okay, thank you.
Thank you.
Kevin?
Yes, that was a bit related. It looks a bit, or in terms of explanation, that you could have something like an avoidance strategy, when you feel that the hospital is crowded. And I was wondering, because this is maybe something you can discuss or tried or asked to healthcare workers. Is that something that you did? Have you had the opportunity to discuss these results with healthcare workers to see whether it matches with what they feel or how they behave?
Yeah, I mean, you're absolutely right. It would be really interesting to do that. I've only discussed it with the healthcare workers who work in our teams, like here at Cnam or at Pasteur. So no, I haven't been able to get a sort of good like picture of like a day in May 2020 and what that would mean for like how you're avoiding people, how much time you're willing to spend in contact with different types of people, that kind of thing. I think that would be really interesting to do.
And the avoidance strategy would make more sense for patients than healthcare worker, I would say.
Yeah, so, I suppose so.
That's not so obvious from your data, or is it?
So if I come to here, so if the patients are, if it seems to be more density dependent, I would say I would interpret that as the patients don't have to be in contact with each other, and therefore they only are when the density goes up. Whereas if we consider everyone altogether, which is kind of largely dominated by healthcare workers, then those healthcare workers have to be in contact with patients, and therefore even if the numbers of patients isn't high, they would still have to be in contact with the ones that are there and other healthcare workers. Yeah, no, probably it would be dominated by healthcare worker interactions, this part, because they form the largest proportion in the population. So under those circumstances, the size of the population probably doesn't vary that much, and the number of contacts that they have to have would be like much more constant, which is something that we saw in the previous analysis. I don't know if that came up last time you presented this, Laura, but the healthcare worker behavior is much more consistent than patient behavior.
Thanks.
Merci, George.
Merci.
Peut-être d'autres questions. Ouais, juste pour apporter un élément complémentaire, je sais plus, j'ai pas l'impression que tu l'aies dit, George, mais en fait, c'est un peu une question de modélisateur, cette histoire de fréquence et densité-dépendance. Mais quand même, à bientôt, Kevin. Mais quand même, quand on regarde, George avait fait une sorte de petite revue de littérature de tous les gens qui ont fait, rien que sur les gens qui ont fait des modèles Covid à l'hôpital. Et en fait, il y en a une certaine proportion qui ont fait des modèles fréquence dépendants, d'autres qui ont fait des modèles densité dépendance. Et en fait, personne ne justifie jamais son choix. Et ça a des conséquences importantes sur les prédictions qu'ils font après, leurs recommandations sur l'efficacité des mesures, etc. Donc, c'est ça qui a motivé ce travail, en fait. C'est de se dire, peut-être que c'est bien de réfléchir et de regarder à quoi ressemblent les données avant de faire ces hypothèses-là. Voilà.
Merci.
De rien. Bon, et la réponse, c'est que c'est pas simple. Voilà. OK. Eh ben, si personne d'autre n'a de questions, on peut passer à la deuxième présentation, peut-être.
I'm Juan Carlos. If you'll excuse me, I'll also present in English. My French is not there yet. This study is on factors associated with mosquito-borne disease protective behaviors. This is a cross-sectional study in metropolitan France. So let me start with the context. Tiger mosquito population and MBD risk increases yearly in metropolitan France. Here is some very interesting data. First, let's talk about mosquito populations. The establishment of the tiger mosquito per department in metropolitan France has been going on for many years. These are just the maps from 2012 all the way to 2023. You can see that the tiger mosquito was well established in France by 2020, perhaps. And now in 2023, we get even more granularity. This is all data from Santé Publique. And you can see how the tiger mosquito has spread very successfully. It is an invasive mosquito that comes from Southeast Asia, and it has spread successfully in all French territory mostly. The north, there's still parts where it's not established yet. However, there is literature that suggests that it will, by 2030, have colonized France. Now, let's talk about the imported MBD cases. So, since mosquito-borne diseases are not endemic in French territory, imported cases of MBDs are very, very important. Here we can see from 2012 or all the way to 2024 until April, and we can see that we reached a peak of 2,100 imported cases of mainly dengue. You can also see some slight chikungunya, Zika, but these are not high numbers yet. And on 2024, something very interesting happened. We have over 1,200 imported cases just until April. This suggests that we might be we might surpass the peak very early, our last peak very early during 2024. And the important part about the important aspect of MBD imported cases is the fact that since MBDs are not endemic in French territory, that means that transmission, in very simplified terms, occurs when travelers introduce the virus locally in metropolitan France. Since the mosquito population is high enough and it concentrates on very dense urban areas, then these people get bitten by a mosquito. And that mosquito, after an incubation period, can transmit that to another individual who was not sick, had not been sick with an MBD. And that's how we go from imported cases to locally transmitted cases. This is quite key because France is a hotspot for international traveling and for migration. We can see this here as imported MBD cases. And also there are a lot of high profile events going on in France very frequently, say the Olympics. In fact, we already have locally transmitted dengue cases from 2019 to 2023. You can see that we reached our peak on 2022 on 65-ish locally transmitted dengue cases. And here are a few more data points to contextualize the issue with mosquito-borne diseases in metropolitan France. 54% of all locally transmitted dengue cases in mainland Europe since 2010 were in France. This is data from the ECDC. The second runner is Italy, by the way. And the first locally transmitted dengue case in Ile-de-France happened on October 2023. It carried a response from government too, which was fumigation. Now, what can we do about mosquito-borne diseases? First, we're going to talk about mosquito-borne MBD protective behaviors. These are individual practices that reduce mosquito biting or that target mosquito populations. Say, for example, wearing long sleeves, wearing repellents, using mosquito coils, and also removing stagnant water. It is notably hard to measure the efficacy, the effectiveness of each of these different practices in reducing mosquito-borne diseases. However, we can safely assume that frequently engaging in multiple practices decreases MBD risk. That is, by decreasing the population of mosquitoes within your context, or that is by reducing the mosquito biting frequency on your shelf. Now, regarding the literature, past research in mainland France is very scarce and also limited to southern regions. So we're going to focus on one paper, which is by Jocelyn Rod et al., 2012. They had a sample of 1,500 individuals. These were adults from these three regions, including Corsica. And these are the negative predictors that they found on protective behavior frequency. They only looked at protective behavior frequency. They didn't look at the specific practices. So say, for example, a negative predictor was being a man. Another negative predictor was having secondary school compared to college or higher. And another one was residing in a place, in a region, where the tiger mosquito was objectively rare. That also varies depending on which region specifically, but they were all negative predictors. Here we have the positive predictors that they found. This would be biting frequency and perceived presence of tiger mosquitoes. All ORs right here are adjusted, and you can see slight differences, but we're not going to go very deep on the results of that so that we can look at our results over here. Two things to point out. First, again, this study was only looking at protective behavior frequency, and also it was on southern regions. Now, what is our objective? Our objective was to examine factors that influence protective behavior in all metropolitan French regions. And we'll do that by analyzing a cross-sectional knowledge, attitudes, and practice survey via mixed effects. Our sample is about 2,000 individuals. Regarding representativeness, our sample is representative according to age, sex, region, and CSP based on census data. We'll look at that in the next slide. Eligibility, just mainland residents over 18 years old participating in an online paid panel. That online paid panel part, that is one of our limitations. And also data collection was done through an online self-administered survey in November 2023. Here's the description of our study population. The thing that I want to point out is that these percentages, both in sex, age groups, region, and CSP, emulate the ones from the last French census. Now, regarding our data preparation. Our data preparation and analysis were pre-registered in the Open Science Foundation. Our missing data was addressed beforehand via forced answering, so we don't really have missing data that we will have to approach in any other way, imputation or so. Data exclusion, we have none, and transformations, we created indexes and we collapsed variables. I'll point that out in these next slides. So first, our study has two outcomes. Understanding these two outcomes is key to interpreting the results. Our first outcome is the count of protective practices. So this is a count of unique practices out of a list of common MVD protective practices, which include free text. You can see right here what's the question that we asked our participants, and here are two of the possible answers. We had a list of 9 possible answers, and they also had free text where they could bring out their own practice if it wasn't on the list. This list includes very common practices such as, again, removing stagnant water, which is one of the most common MVD protective practices, wearing long sleeves, wearing repellent, and so on. And the count is just goes from 0 to 10. Our second outcome is frequency of protective behavior. It's a 3-level ordinal on last summer protective behavior. It goes from never, a few times, and several times. Here you can also read our question. And now, let's talk about our predictors. First, place of residence. It's a combined city size and region. So we asked for participants, what's your city size? We gave them small town, large city with the attached numbers, more than 20,000 people and so on. And we combined that with the region they were from. That's how we got our place of residence. And some examples is, for example, a village in Bretagne or a large city in Ile-de-France. We have 52 possible values. And then we have financial difficulty. This is a binary, no, yes. This one is collapsed. We asked our participants if they experience financial difficulties, such as not being able to pay your mortgage and so on. And the response categories were no, yes sometimes, and yes often. We collapsed both yes responses due to sample size. Then we have confidence in health authorities to manage health crisis. This is a continuous variable. It goes from low confidence to high confidence. That is from 1 to 10. It combines confidence in national and regional municipal authorities. Here are the questions. Both items are very similar, and we combine these two in order to have this one variable, confidence in health authorities to manage health crisis. These predictors are informed by literature. This one particularly very informed by a lot of literature on the COVID situation. And we got a few more. MBD knowledge score, it goes from very low, which is -4, to high knowledge, which is 5. This combines two questions. One, knowing that not all mosquitoes bite. And two, knowing which diseases are vectored by mosquitoes, given a list, and not identifying wrong diseases such as, say, diabetes. We can talk about that variable at the end. I'm very happy to go more in depth on that. We just wanted to have a quick variable to summarize what is MBD knowledge, which is again a very hard task to do. Biting frequency, an ordinal, it goes from never or almost never to sometimes and often. It just states how often you perceive that you've been bitten by mosquitoes. And then we have perceived MBD threat. This one is also quite interesting. It's a continuous variable. It follows the same procedure as confidence in health authorities. This continuous variable goes from low to high threat from 1 to 10. And it combines two aspects, which is perceived likelihood and concern of MBD infection. Our covariates, educational level from no diploma all the way to Bac 7, PhDs, postdoc, etc. Sex, men or women, it's a binary. Age here in years, chronic disease status, a yes or no, and the history of MBD. That is, if you've had any MBD, yes or no. Now, our model selection, our general strategy was pre-registered, and it goes from having a theory-driven, fully specified model with random slopes and random intercept, and then going successfully through a random intercept model, fixed effects models, reduced models, and overall a best fitted model. So this is how we're going to present it. We compare the performance of our models via LRT, so likelihood ratio test. And now we can talk about the results. Here we're presenting our best fitting models, but first, let's look quickly at the descriptives. This is our table of our KAPs, our knowledge, attitudes, and practices on mosquito-borne disease prevention. I would like to point out first our count of protective behavior. These are means and standard deviations over here. Our count of protective behavior has a mean of 2.5. That means we got more people between 2 practices and perhaps 3 practices of mosquito-borne disease prevention. And we also have our mosquito-borne disease knowledge scores. Note that these two are in different ranges. The scales are quite different. So for count of protective behavior, we go from 0 to 10. And for mosquito-borne knowledge scores, we go from -4 to +5. Something key to note right here is that interestingly, our mosquito-borne disease knowledge score also is partially measuring misinformation. So in order to get to -4, you will have to be misinformed, believing that, say, COVID or diabetes is also vectored by mosquitoes. That's how you get to the lowest part of the range. For mosquito-borne disease knowledge score, we also have a 2.5 mean. And now, here are the perceived likelihood of contracting a mosquito-borne disease. It goes from 1 to 10, not likely at all, very likely, or much certain. And then we have concern of contracting a mosquito-borne disease. Again, it goes from not concerned at all to highly concerned. Our median here is about 6, and you can see our interquartile range over there from 4 to 7, from 4 to 8. And then we have confidence in national authorities and regional authorities with a median of 7 and an interquartile range of 6, from 6 to 8. So first, our count. Our count model is a negative binomial mixed model. It's negative binomial models let us model count outcomes without assuming the Poisson distribution, which was key for this one. Now we also have random intercepts for place of residence. That is because by design, our sample is naturally clustered. We had to address that clustering in some way. And also our model is zero inflated. It's zero inflated because we have excess zeros, also called structural zeros. And here we do make one assumption, one key assumption, and that is that our zero counts, the probability of having a zero count is not the same for all observations. It varies by biting frequency. So here is our first model. We're modeling count of protective behavior. Here I have just highlighted our significant predictors. The one that it's a heavy hitter, I'd say, it's biting frequency. Often biting frequency is sometimes that too. We have then MBD threat and MBD knowledge score, chronic disease status. And I would like to point out this very specifically. Beyond statistical significance, we can see that education is a very interesting predictor, as the successive levels also carry some increase in protective behavior, in the count of protective behavior. All of these predictors resulted in positive predictors, by the way. And also you can see that there's a slight dip on back +5, but it picks up again on back +7. And that slight dip on back +5, it doesn't go below that of back +2. So very interesting variable, very interesting behavior here with the estimates that we have. Although if we just stay on the statistical significant aspect of it, the only one is back +3 and 4. Here, let's talk about the zero inflated model as our negative binomial zero inflated model. The idea is that it's a two-part model. We model counts on one side, including the zeros, but we model our structural or excess zeros on a zero inflated model over here. Biting frequency was a negative predictor of zero counts of protective behavior. That is to say that if you get bitten by mosquitoes, they're often or sometimes, as compared to our reference category, which is never or almost never, you are much less likely to have a zero count. And here is personally an interesting variable. We have random effects by place of residence. Again, place of residence is this combined variable when we use both the size of the city and also the region where it is. So we get 52 possible values, which are, for example, a large city in Ile-de-France or a medium-sized city in Corsica. And here you can see our residual variance, our random effect variance, and more importantly, our adjusted ICC, our intra-class correlation coefficient. And what we found is that place in our model explains a minuscule proportion of the variance when we're controlling for all of these other factors over here. So at this point, I wouldn't look very deeply into the role of place within this moment. However, I do want to say that the geographical variables that we use, say region, department, or some other sort of index for that, is probably very key in understanding protective behavior. However, in this model, this is not what we're seeing, and we're going with the data. We do keep our random effect one because our sample is still naturally clustered by design. We should address that sort of clustering in some way, and also because when compared to a fixed effect models, we really get we don't get a better performance from the fixed effect models. So we are actually keeping this one. Now, regarding fit, we believe that this one model has a very strong fit, an under dispersion of 0.93, not significant, zero inflation of 0.99, not significant. Here, in these two specific aspects, we would be looking for a 1, but that would be utopical. So a 0.93 and a 0.99 is what you can expect from real world data. This is after, of course, the fact that the under dispersion and the zero inflation are both addressed by the negative binomial part of the model and the zero inflation part of the model. For multicollinearity, we're using variance inflation factors to account to measure that. We got very low BIFs, below 1.5. The lowest threshold that you could find in the literature is 3 for very, very low. And it would be concerning if you go over 5 or 10. That would be the scale where we're working on. Regarding uniformity, we use a Kolmogorov-Smirnov test on residuals. Again, p-value not significant. And the one thing where we have a concern is our residuals could be improved. I'm happy to talk about those residuals. We do have a slide at the end, but right now we can talk about the alternatives to the model that we have. So we model all these different possibilities. Say, for example, the fact that our zero inflation may vary not by biting frequency, but by thread or by any of our other predictors, and we get a worse fit. Same thing, we also model the possibility that our zero inflation, our excess zeros, are the probability is the same for all observation, worse fit. A zero inflated Poisson mixed model and negative binomial not zero inflated mixed model. Though models were quite interesting. So zero truncation is an alternative to zero inflation models because they assume that the processes that give us zero counts are different. We model that it's just like we have a slight reduction in model fit, but more importantly, zero truncation may not be theoretically justified for our variable and the way that we understand zero counts in mosquito MBD protective behavior. And we do have one alternative with this Compois mixed model. Here our argument is that the negative binomial is more interpretable, but it is true that it improves our fit slightly, but it doesn't address the residuals, which are the one concern that we have with this model. So we're keeping the zero inflated negative binomial mixed model as we presented it, and these were all the alternatives that we tried. Now let's talk about frequency. For our frequency outcome, we have a cumulative logit mixed model. Cumulative logit models let us model ordinal outcomes, but still considering the ordering of the factors and we can still do it within the same model, as opposed to, we'll see some of the alternatives, but say linear regressions, they have issues as you don't really meet the assumptions. And then multinomial logistic models are much more complex, as you have to, you necessarily have different models, different equations for each of the levels. We also have random intercepts or place of residence, same reasoning as before, and very importantly, unstructured thresholds. This is one of our key assumptions, and that is that the distance between, say, our ordinal outcome categories from never to sometimes to often, these are not equidistant. It's not the same distance, and we're also not supposing that these distances are symmetrical. Many other ways of modeling ordinal outcomes do that. If, say, you had a Likert scale as an outcome, then you might think that these are somehow structured thresholds. They're equidistant or they're symmetric. We're not doing that assumption. Here is our model for the frequency of protective behavior. First, just to get it out of the way, if you're not familiar with cumulative logic mixed models, I wasn't personally. You do get thresholds, which are work as intercepts. They're rarely the target of inference, and they really estimate the response probabilities. They reflect the increasing odds of being in higher categories. So you could read that. You could read these as the intercept between never and a few times, and then between never few times going to several times. That's how cumulative logic models work, and that's why we have these two here. We're not gonna go deeper on this one because it would be interesting in our predictors. Our predictors here are perceived MVD threat. It goes from 1 to 10 again, biting frequency, financial difficulty, and age. You can see that here we have some similarity to the count model. And also I would point out that financial difficulty is just slightly over the p-value, but that is still a slightly below the p-value, but that is still an interesting estimate that we got right there. And again, same read as with the count model, our residual variance, our random effect variance, and our adjusted ICC. It goes on to show that within our models, place really explains a minuscule proportion of the variance. But here for this model, we can look at that just a little bit more deeply. This is the effect of places via conditional modes. Random effects are really not parameters, so they cannot be estimated in the traditional way. We don't really get an estimate for random effects. However, we can get, for these models, conditional modes. Conditional modes are modes of the distribution for place given the data and the estimated parameters. As it stands, it is our best guess at the effect of our random effect within our model. We can also get our 95% confidence intervals based on what we call conditional variances. And here you can see from all the way from each place of residence, which we have 51 values now. And again, village in Bretagne, large city in Ile-de-France, etc. And we can see that only one of them goes beyond the statistical significance. You can guess which one it is, and we do have the names for each of the places. Regarding the figure, it is not feasible to actually name each of them right here. Here are our top 10. So a higher conditional mode, that is being on the right side of this table, that means that these people within these places have a higher chance of being in the higher categories of our response variables. That means that they would be closer to the often frequency or to the sometimes frequency as opposed to the never or a low category. Here we can see that that one place which is statistically significant is Ile-de-France, large city. We can see also like the rest of the place, say the Occitanie, etc. However, this is to say we're still within a very low variance. So the fit. Here we do have some interesting model fit situation. There's ways to address that. All those ways have some sort of drawback, but multicollinearity for thread is high. It has a BIF of over 10 that would be very high. The proportional odds assumption of the model is partially unmet for thread and biting frequency. That means that the effect of thread and biting frequency as predictors is not the same for every threshold that we have. It's not the same from never to sometimes as it is from sometimes to often. And conditional numbers of Hessian over our threshold, that would mean that we might run into singularity issues, but it's still within what is acceptable there. These are the alternative approaches to our model in this case. I already talked about multinomial logistic mixed models. In this case, we lose information by ignoring the outcome ordering. We also lose power. It is harder to summarize and communicate, but it is a fair alternative. And also the possibility of doing a partial proportional odds mixed models. That would be the same model that we have, but we address that unmet assumption specifically for threat and binding frequency. The drawback here is that we would not get estimates for those two key variables. Key regarding the literature, key regarding our other model where they were significant, etc. All the other possibilities like a linear mixed model, sequential adjacent category, they are just not, there's no strong argument for this. We also tried other link functions and thresholds. This is still the model that performs better. And here we have a little summary of what goes on. We have binding frequency, MBD threat, and age as predictors of both count and frequency. That is, if we maintain our assumption that MBD protective behavior is a function of both count and frequency. We have financial difficulty for frequency and education, MBD knowledge score, and chronic disease status for count. Thank you so much for listening, and I'd be happy to chat.
Thank you, Juan Carlos. We're running a little bit over time, but there's time for maybe one or two very quick questions. Yeah, Simon, Lisa.
Can you hear me?
Yeah.
Okay. Maybe you mentioned it, but maybe I lose information. Why did you choose in the first models? Is it the zero inflated model? It was because you had a lot of person who didn't apply the protective behaviors, or what was the reason to use this type of model instead of a Poisson regression?
Yeah, so regarding the Poisson regression aspect, a negative binomial is pretty much a Poisson regression. Statistically, you would even argue that the Poisson regression is a special case of a negative binomial. Regarding zero inflation, it's a very interesting topic, but there is a lot of ways which you can just partially address the fact that you might have what they call, what we would call structural zeros. Structural zeros or excess zeros does not mean that you have too much zeros or that you have many of them. It goes a bit deeper on the fact that the predicted zeros and the observed zeros, there's a ratio there, and you can just you have to address that in some way. Otherwise, your estimates within a Poisson or a negative binomial non-zero inflated model, they would be severely limited right there. There's a lot of very interesting takes on that. And also we have a zero inflated model, which is one alternative that is different from a zero truncated model. Zero truncated models would assume that the zero counts go on one side and the non-zero counts are a different model totally. But our zero inflation model, it assumes that the excess zeros or the structural zeros go on one side and zeros and non-zero counts go on the other side, and that's why these are two-part models. Yeah, we have a bigger justification how we reason the zero inflation, but also it just provides a whole lot of goodness of fit for our specific case. That is also that we something that we demonstrated as I run all the other possibilities, non-zero inflation and zero truncation. Thank you.
Thank you. Thanks. Aurélie?
Hi, it's Melissa.
Ah bah c'est trop fort.
Surprise. No, I just have so I have a question, but it's actually it's more related to the first figures that you showed of the number of imported cases in France and the number of local transmission cases. I don't know. It looked quite surprising because So yeah, on this slide, you can see that in 2022, the number of dengue cases is imported dengue cases is very low. If I remember well, travel bans during the COVID-19 pandemic mostly happened during 2020 and 2021. So I'm wondering why is it so low in 2022? And when you look at the next slide on the number of locally transmitted cases, you see that it's very high in 2022. Meaning that the local transmission was very high and was that high that it had to compensate the lack of imported cases. So is it due to the fact that in 2022 the surveillance system was not good enough and there was not a good detection of imported cases? Or I don't know if you have I'm just curious about this point, but I don't know if you have the answer.
Yeah, the relation between imported cases and locally transmitted cases is it's its own topic in itself. We cannot really draw a sort of like linear relationship, as in like more important cases means necessarily more locally transmitted cases. Also because you have to factor in the possibility of outbreaks, right? So say, if I recall correctly, on 2022, the issue was that we had a big outbreak, which included, I don't know, over 40 people in just one sort of like outbreak site. Geographically, all were very close and so on. Then you have to factor in the fact that, say, for example, these important cases, where are they even going? Because if they're going to places where the mosquito population is smaller, or they're not engaging in the activities where they would be in risk of being bitten, then it gets very muddy like that. I still think looking at imported MBD cases is extremely important, especially due to the very characteristic nature of France, right? International travel, migration, high-profile events, year-long. But the reality is that we cannot draw a very direct line over here. I do think that quick reaction from public office, it's needed, it's key here. But the reality is that France, metropolitan France, is still immunologically naive and behaviorally naive, I'd say, population regarding MBDs. But that is an amazing question. There's people who are working like exclusively on that relationship with the about imported cases and locally transmitted cases. I saw Jose.
Yeah.
Thank you for that.
Thank you.
Yeah, I was just going to add one last note on that, and that's that we just attended a conference all about mosquito-borne disease in metropolitan France yesterday. And they reported that there was a very interesting correlation between imported cases in metropolitan France and ongoing mosquito-borne disease epidemics in the other overseas departments. So, for example, I think there has been an ongoing epidemic of dengue over the past 2 years in La Réunion. And so it was either La Réunion or Martinique, I don't remember anymore, but
Martinique and Guadeloupe, yes.
Oh, okay, Martinique, yeah, because in the Caribbean. So what we also see is how traveling to these countries or to these departments also ends up having this relationship with metropolitan France. So with these imported cases, like in 2022, there wasn't an epidemic going on at the same rate. And so that might also have to do with why we didn't see the same increase in imported cases in 2022 as we see in 2023 and now 2024.
Most of the important cases are also from Martinique and Guadeloupe, from French territories. So yeah, thank you.
Ok. Bon, écoutez, vu qu'il est 15h10, si je ne vois pas d'être main levée, je pense que je vais vous proposer de remercier encore nos deux orateurs d'aujourd'hui. Et puis, vous libérez tous. Voilà. Et on se revoit à la fin du mois de mai pour le prochain séminaire. Voilà. À bientôt.